This is 4.1 still. We're finishing up. This is where we stopped. So we're talking about inverse functions. So I graphed f of x, and then I graphed f inverse of x. But there was an issue because f inverse is not a function. It does not pass vertical line test. It's not a function. The problem was because f was not 1-to-1, so it did not pass horizontal line test. So inverse functions must be 1-to-1. A 1-to-1 function, you already have that written down, but just a reminder, every element in the range corresponds to only one element of the, I should say, domain. Alright, so what we need to do is we need to restrict the domain of f. So I'm going to change f of x just a little bit to make it 1-to-1. So I'm going to just cut off half of it. I want to take, I can either take the right or the left side. It's easier to work with positives, so I'm going to take just the right side of this parabola. So to do that, I'm going to restrict the domain and just take where x is greater than or equal to 0. So I'm just cutting off half of that parabola. So that will look like this. Okay, now let me go ahead and write those points back in the table so I can do f inverse of x. So I'm just copying down these points of 0, -2, 1, -1, 2, 2, and 3, 7. So then f inverse of x, I can just switch my ordered pairs, the x and y's. And graph those. Okay. And now I have a function. So I made f 1-to-1. So then I got a function for the inverse. We're going to find the inverse, so the equation of f inverse algebraically, so like we did on the warm-up. So those are the 4 steps we talked about on Wednesday. So step 1, write y instead of f of x. So we will talk about this domain restriction here in just a minute, but for now we're just going to look at x squared minus 2. So y equals x squared minus 2. Switch x and y. y. Alright, so what would I want to do first? Yep, I want to add the 2. So that's x plus 2 equals y squared. And then how do I get y by itself? Good, square root. When you're solving and you have to use a square root, you have to write plus or minus. So you have to get plus or minus x plus 2. Okay. This is where the domain restriction comes in. So since I just took the right side of that parabola, that x is greater than or equal to 0, then I just need the positive part of the radical x plus 2. If I had decided to take the left side, so if I had made this less than or equal to 0, then I would choose the negative part of the radical. Okay, so this comes back down to play. Right, so that domain restriction came in to tell me I just want the positive. So, and then the last step, replace y with f inverse of x. So that's how we get square root functions to be inverse functions of quadratics, because you have to take the square root when solving a quadratic. All right. So if you look at this function, square root of x plus 2, and let's say we were going to graph that. Well, the graph of this would shift left 2 from the parent function. So let's look at the graph. And it looks like I shifted left 2 from the parent function, and then this graph here in blue, that's the graph of a square root function. Okay. Questions about that? Okay. What we're going to do now is talk about verifying that 2 functions are inverses of each other. So when you see the word verify, another word for that is prove. So when you talk about doing proofs, the important part is the steps. The important part is the middle part. You know the beginning and you know the end. You know what you're trying to get to. It's how you get there. So we're not writing out like a 2-column proof like geometry. We're going to just show our steps, show our work. So when you do an algebraic proof, you're just working out the problems and showing all the steps. So to verify algebraically, we're going to use compositions. So that's a composition is where you put a function into another function. Okay, you have to test both directions. So you have to put f inverse into the f of x function, and then you have to put f into f inverse. Each time when you simplify, you're simplifying and wanting to get x. You're not solving, you're not trying to get a value, you're not trying to get 0, you're wanting to get x. You have to do both ways, so it's important to recognize that both composition verifications must be performed. You have to do both directions. y equals x. You have to show the steps, and you have to do correct order of operations. So you have to actually do what's correct when solving. Okay, so I want to prove that g of x is the inverse of f. So I'm going to do f of g of x, and then I'm going to do g of f of x. I have to do both ways. So this first one, g of x is the inside function, so this goes into the x of f of x. Okay, so this is what I'm talking about. Do not just write x from here. Yes, I'm sure you could look at this, do it in your head, and know it's just going to be x. But what's important is showing the steps. Okay, so I need to do this correctly as well. I cannot subtract 4 yet until I get rid of the parentheses. I can get rid of the parentheses by canceling my 3's. So I canceled the denominator. That's just leaving me with x plus 4 now, minus 4. And then 4 minus 4 is just x. Okay. Now I need to do the other way. And I need to plug f of x into the x of g of x. Okay, you have to simplify this correctly. You cannot cancel these 3's yet until you simplify the numerator. After the parentheses, there's just a plus sign. You're just adding. So if you're just adding or subtracting, you can get rid of the parentheses. Okay, and now I have like terms to combine, so negative 4 and positive 4 is 0, leaving me with just 3x on top over 3. And now you can cancel the 3's. Okay, so since both compositions simplify to x, I can say that g of x equals the inverse of x. So this was the word, this is my answer. Okay, questions about that? Okay. So I'm going to do the same thing. This is the two functions I just got done graphing. Now we're going to prove that they are inverses. Okay, so I have to do f of g of x and g of f of x. Alright, so first one is to plug g of x into f of x. square a square root, you get just what's underneath. And then positive 2 minus 2 is 0, so you get x. Okay, so that one, we're good. Now we go the other way and plug f of x into g of x. So to remove your parentheses, you have a plus 2, so you're just adding. You can go ahead and get rid of the parentheses. So negative 2 plus 2 is 0, so you get square root of x squared. So before you write x, we need to talk about this a little bit. So you're squaring x, which means after you square it, it's going to be positive. So technically, you could have negative values for x because you square it and it becomes positive. So what this is square root of x squared is the absolute value of x, which is plus or minus x. So when you square root x squared, the answer is plus or minus x. We noted, though, this. X has to be greater than or equal to 0. So I only care about the positive, so therefore I can say equals x. This is part of the work, though. Okay? So if you jump right from here to here, you will lose a point. You need to show that you know that the square root of x squared is actually plus or minus x. Remember, when you're proving, it's the middle part that counts. Okay? So you do not want to jump just from square root of x squared to equals x. It's only equal to positive x because of the domain restriction. If this weren't there, x squared greater than or equal to 0, if that weren't there, then you could not say that they were inverses. You would have to leave your answer as plus or minus x. So I think you should make a note about that rule. Let's finish this up though. Let's say, okay, so g of x does equal f inverse of x. Then we have a rule that if you do the square root of x squared, that's the absolute value of x, which is plus or minus x. Questions about that? Okay. So I'll give you a second to read the directions here. We have lots to do on this problem. says is find the inverse of each function. So we're going to find the inverse, but if you read on, it says state the implied domain and range as you begin. Okay, so I'm going to start here. I'm finding the domain and range just of the original w of x. Okay, what type of function is w of x? X squared minus 1 is quadratic. Okay, so typically quadratics are, the domain is all real numbers, but I have a restriction. So this is my domain. Okay, x squared is greater than or equal to 0. So that means bracket at 0 goes to positive infinity. And now think about what the graph of that looks like. So x squared minus 1, you shift which way? Down 1. So your new vertex is at 0, negative 1. So that means your range, you start at negative 1 and you go up, so positive infinity. So that's where you can get your range. Okay, so now I want to, it says use these to say the domain and range of the inverse function. I'm going to go ahead and find the inverse first now. So now I'm going here, find the inverse function. Okay, so write y instead of w of x. Switch x and y. Add 1 to both sides. Square root, when you write in the square root, you have plus or minus. But I know that it can't be both, so I have to use that domain restriction. And do I want the plus or the minus? The plus, because it's greater than or equal to 0. If it were less than, you would want the negative. So w inverse of x is x plus square root of x plus 1. Okay? Okay, so we had said find the domain and range as you begin and use that to find the domain and range of the inverse. Remember, inverse functions switch your ordered pairs. So technically that means you're switching the domain and range. So my domain of w of x is 0 to positive infinity, so that becomes the range of its inverse. The range of the original was negative 1 to positive infinity, so that becomes your domain. And think about that. So this is a square root function. So for your domain, when you had to find domain of this, it was x plus 1 greater than or equal to 0. You had to write that inequality, which means x is greater than or equal to negative 1. Okay, that's how you'd write that in interval notation. And then it's a square root function where its initial point starts at negative 1, 0, so 0 for y. and then positive infinity. So yes, you can just switch them, but think about the function to make sure that it makes sense. Because if it doesn't, then you might have messed up on your original domain and range. Okay, so I did this. The last thing, prove by composition your inverse function is correct. So lots to do in this problem. Make sure you're keeping things organized. So I have to do W of W inverse of X. And then I have to do W inverse of W of X. Okay, so I'm plugging in the inverse into the original. So the inverse, I got square root of X plus 1. Okay. Square is square root. You get what's underneath. Here your work is important because this is how you're checking that your inverse is correct. If it does not simplify to give you X, then you know you did something wrong. And I wrote something wrong here because, right, I think that's just X plus 1, not X squared plus 1. I wrote that wrong. So X plus 1 minus 1 equals X. Okay. Now the other way. So plug in the original into the inverse. You're just adding after the parentheses, so you can drop the parentheses. So square root of X squared. Okay, remember the rule. Square root of X squared is absolute value of X, which is plus or minus X. But X has to be greater than or equal to 0. So it is just X. Yes.
I know we have to put in this that step, but like, do we have to put in the one that says absolute value of X, or can we just go to
Like here to here? Yes, that's okay. I don't want you skipping too many steps because that's what's important, but yes, that is okay. All right. So then I did my verification. So they are inverses. Yes.
if you do all the steps right, will it always come out as the inverses?
Yes, in this case, yes, because the work was finding the inverse, and then, so you're basically, this proving is you're checking that you did this part correct. So if you did this part correct, then these will give you X and X. There are some questions that could say, are these two functions inverses? So you do this proof, and if you don't get X and X, then they're not inverses. But like this problem, it's telling you this is true. It says prove this, so it's telling you that's true. So you should simplify and get x of x. Okay, any other questions? Okay. Let's look at this. Again, kind of lots of steps here, lots of different things it's asking for. So it gives me the inverse, and I'm supposed to graph both and dash in that line y equals x. Okay, so if I graph f of x, what type of function is f of x? Cube root. So you might need to brush up on your parent functions a little bit. We didn't do a whole lot of cube roots. You can also use the calculator to help you. So it has an inflection point, so not a vertex because it doesn't change like from increasing to decreasing or decreasing to increasing. It's called an inflection point. And so I shift, so this is the inside right 7. So I have an inflection point at 7, 0. Okay. So when I go to graph this, I have this inflection point at 7, 0. And then cube roots. So if you go from your inflection point up 1, the cube root of 1 is 1. So right, if you go right 1, the cube root of 1 is 1. So up 1. If you go down 1 or left 1, the cube root of negative 1 is negative 1. So you go down. So up and right, down and left. Then let's skip because we're doing cube roots, so perfect cubes. So let's skip to 8. So if you go right 8, you would go up 2. If you go left 8, you go down 2. So from your inflection point, I'm going to go left 8, 1, 2, 3, 6, 7, 8, down 2. The next cube root is 27, so that's not going to fit on my graph. Okay, so then I look at the inverse. What type of function is the inverse? Yep, cubic. Okay. It also has an inflection point. And so this time the 7 is on the outside, so I move which way? Up 7. So 0, 7 is the inflection point. Okay, this time we're cubing. So from your inflection point, if you go right 1, 1 cubed is 1. If you go left 1, negative 1 cubed is negative 1. If you go right 2, 2 cubed is 8. If you go left 2, negative 2 cubed is negative 8. Okay. It also says sketch in the line, so dash the line y equals x. So that's the line, remember, it starts at 0, 0, and you're going up 1, right 1 the whole way. So you have points at 1, 1, 2, 2, 3, 3, negative 1, negative 1. I do need to make sure that I label my graphs so we know which one's the original and which one's the inverse. Alright, it said note how the graphs are related. So you could say something that, like how your points switch, so the x and y coordinates switch at every point. But since we have this line, I want to say they are reflected over y equals x. So they're reflected over that line, y equals x. Remember, lines of reflection are like lines where you would fold. So if you folded this graph in half based on this line, then the graphs would overlap. Okay, so I'm here. Then verify the inverse function relationship using a composition. So verify they are inverse. So I have to do f of f inverse of x, and then f inverse of f of x. So I'm plugging in x cubed plus 7 into the cube root of x minus 7. I'm just subtracting so I can remove my parentheses. Seven minus 7 is 0. Okay. All right, odd roots, cube roots. Those can be positive or negative, so I don't have to worry about that plus or minus issue here. When it's cube root, you don't have to worry about it. It's just x. Okay? You don't have the plus or minus here because it's an odd root. All right, now the other way. So now I'm plugging in the cube root of x minus 7 into x cubed plus 7. Okay, if you cube a cube root, you get what's underneath. And negative 7 plus 7 is 0. So again, you're left with x. Any questions about that? Okay, that's the end. I will go back and go to the very first slide that we did today if some of you did not get all of that written down. So I will go back to that. But that is the end. Just a minute.